This is the last stuff we covered, so probably needs the least review, but just for completeness sake, let's go over what we talked about in Unit 12. This was inference for linear regression, and we're always making inference on the slope of a line. The null hypothesis in a hypothesis test is that there is no association, and therefore you're going to have a slope of 0. So remember, any positive or negative slope means there's an association of some kind, but the slope of 0 means that there's no association. The change in one has no bearing on the change in the other. Confidence intervals estimate the true slope, and your hypothesis test just tests for whether or not there's an association. Here are the specific formulas for your confidence interval on the left, for the test statistic on the right. And once you have your test statistic, it's going to be a t-test, and you will have to have your degrees of freedom. Do I mention that here? No, but your degrees of freedom is going to be n-2 for this, so it's just a little bit different. A lot of this is going to be conceptual stuff, same is true as with everything. I will say this only counts for just as much, at most 5% of your multiple choice questions. So it is definitely one of the less important concepts to cover. But our conditions, it must be, if you remember Liner, it must be linear, it must be independent, or another way of talking about independence is that if you have a, if you're sampling without replacement, you have to draw less than 10% from the population. So independent is another way of talking about the 10% test. N means it must be normal, and we check that with the normal probability plot, which we're looking for a straight line on the normal probability plot. We can also look at the residuals, and the residuals should be normally distributed. Okay, different ways of looking at that. Equal variance, that's what the E stands for your residuals. You should see the same kind of spread the entire way. It shouldn't grow bigger or get smaller along the way. And R is random, pretty straightforward with that. Okay, let me see how many questions we have on this. Wow, I have more than a couple. 1, 2, 3, 4, 5, 6. Okay, so here we go. Let me just let you try this one on. This also was dealing with transformation of data and transforming nonlinear into linear stuff. So that's what this first question is related to. Right, a minute ago I said this is transforming data. It's technically not right. We're re-expressing the data to turn it linear, and that's already been provided for us. And when you go through this, you're essentially solving on the right side, and you get 7.01 equals natural log of y hat. And that means we need to do e raised to both, or e raised both, raising both sides. Okay, so e to the 7.01, and that gives us y hat, which in this case will be 1107.7. There's your answer. Okay, let's clear that. Move on to another one. I'll let you guys just try these on. Now, you might have used context clues for this problem, just the fact that we're studying Unit 12, which is on linear regression. And so you might have just immediately jumped to linear regression t-interval and just said, boom, got that. Maybe you didn't think through it like that. It is a linear regression t-interval for slope, but just in general, because you're not going to be seeing these grouped into units on the test. So what you're looking for is, well, let's see. B is correct. I'm not giving you a hard time. I was saying that is it was fair if that was your thought process on this one, but but on. Because you thought you got it wrong. You said, I thought you were actually understanding it. All right. So with this one, what we're looking for right here is like figure out what is actually being inferred. Like, what are we making an inference on? What did you lose? Good luck. So what we're making an inference on right here is the researcher is trying to estimate the mean change in concentration for each increase in 0.1% salinity in lake water. So the idea is that we're looking for a rate of change and we're estimating that change. So the linear regression inference, this is the only one where we're drawing inference about a rate of change, the slope of a line. With everything else, it's a difference of means, it's a difference of proportions, it's kind of an absolute quantity, and this is more of a rate that we're looking for. So that's going to be your giveaway on the real test. This is a fake test. All right, let's try this one. So the 90% confidence interval was given right here. And the important thing is, what is going to make this wider? And just in general, one thing to remember is that your margin of error for a confidence interval, so it's going to be B plus or minus your T star times your standard error. And your standard error is defined as, oh gosh, what's the formula? I'm going to have to go, I don't have this one memorized. There it is. It's S sub E over S sub X times the square root of N minus 1. But the important thing right here is that because this is like with every other standard error we have, so this is true for any inference test, the bigger your sample size, the smaller your margin of error. So the only thing that's going to make this wider, the only thing that's not going to make this wider is if we increase the sample size. We started with 15, going to 16 is actually going to cause our margin of error to decrease. Now, of course, there's a caveat to this, that we could get a data value that changes our standard deviation of the residuals, and then that could throw off the numerator a bit. So it could theoretically be a bigger margin of, or a wider margin of error, even with more data points. But all things being equal, then, and that's what it says here, if all other things remain the same.
Cody?
He was.
Is he on Zoom?
All right, so essentially that's what's going on with that problem. So let's look at another one. So we have our liner right here for the conditions. To be fair, this kind of violates two of them. And it's really hard to pick which one is the better violation. So what I hope that you've come down to is it's either going to be nonlinear or that it doesn't have equal variance. Now, in my opinion, linear is the better choice, that it violated this. And it's not to say that that is the absolute choice and equal variances being met. But it's a tough call between those two, but there's a very clear nonlinear trend to it. So I think that's, in my opinion, the better answer for this one. And yeah, it was entirely split between these two choices.
What's the correct
answer? Linear? Hear my confidence?
But I think on the test, I put equal variance.
Okay, well, and this is one of those 50-50. Hopefully you don't get a question like this, because both of them are being violated. And I might have accepted both. In fact, what I have is a note to myself to double check this on the test, which ones I accepted. I might have accepted both as an answer. And if you got it wrong, you might find that you got this right if you answered one of those two. So there you go.
I have a question.
Go ahead.
So to see if it was independent or not, would it be not independent if there was a pattern or something?
It really, the independence is checked when they describe how the data was collected.
Oh, okay.
So essentially, we're checking the 10% condition. So when you see independent, just think 10%.
Okay.
Now, and this is an important nuance I really want to emphasize as much as I can, and I try and emphasize it in this class, but if the data is collected from independent trials that are truly independent, and that would be something like shooting free throws, just over and over, each one is independent. We can consider it independent. And there's no real population we're drawing from because there's theoretically an infinite number of free throws. So we're not drawing, there's no 10% that has to be met. In that case, we say it's independent. So the 10% condition isn't required. The other thing is, if it is kind of drawing from a population without replacement, then we have to make sure we draw less than 10%. And the idea behind it is that if we use less than 10% of the population, then it's close enough to the simpler calculations that we can consider those accurate enough. Because if we start drawing more than 10%, we have to use more complex statistical calculations for our tests. We get into hypergeometric distributions and things like that.
Would that also be kind of true for the like normal part and the random part? You kind of like see that from like the prompt or like question.
Yeah. I would be incredibly shocked if they ask you to assess normality on a linear regression. If they do, they're going to have to give you some kind of extra plot. It wouldn't be just residual. It would have to be probably a normal probability plot in all likelihood. Yeah. Okay, good questions. Here's another one we can look at.
I had no knowledge.
All right, let's look at this problem. We are looking at situation, and this one actually had some difference of opinions. Well, I mean, a lot of them have difference of opinions, but I will say this. The answer I chose is E. All right, the last one. So the reasoning behind this is that it does not give us an indication that they're coming in with a specific one-tailed hypothesis in mind. So it might say, as an additional sentence in here, the doctor suspects that as your number of miles jogging increases, they have a lower resting heart rate. And that would at least be my hypothesis behind this. I'm assuming a doctor would have that hypothesis, but I'm not calling myself as smart as a doctor here. So if that's the case, that's bringing in kind of your prior knowledge, and you're kind of assuming that it's a one-tailed test. But according to the language itself, it's really just asking is whether there is a linear relationship and nothing more. So in this case, our alternative hypothesis should be that our slope is not 0. That's the best answer. The second best answer would be that the slope is less than 0. So this is not right, but that would be, I would understand why someone chose that. I think if you chose this one right here, then maybe let's kind of think as your miles increase, we would probably expect that person to not have their heart beating as much. So we would expect this kind of relationship, resting heart rate, that is. Okay, enough on this problem. Okay, last one. Here we get to do some calculation. All right, with this, it's important to remember that very little by way of calculations is going to be expected of you. You do need to know how to do the calculations, but it's not going to be super complex. And what we have here is the printout, and we never care about the intercept. So we're interested in this line right here, and the estimate right here is essentially what this becomes right here is B, which is our sample slope, and this is the standard error for our calculation. And the test statistic, T, is going to be b minus beta divided by the standard error. Because our null hypothesis is that beta equals 0, then this basically just becomes b divided by the standard error. And those two values are given to us. It's basically 0.6 divided by 0.051. That's all you had to do. Of course, that's not your answer. When you do that, you will get 11.76. Okay. So again, linear regression is this oddball thing to just tack on at the end, but luckily it requires very little by way of complex calculations. Hey, how about that? That's pretty good. And we're done with all of our review. Tomorrow we will go over some FRQs, and that's about it. After your AP test, now your problem statement is due today. Make sure you're getting that done or asking me questions about it. After the AP test, it'll just be a few days to get your project finished, and I'll give you more information on that probably on Monday of next week. And then after the AP test and your projects are done, you guys are done. So this Friday, while it's still fresh on your mind, I wanted to give you guys your final for the class. Remember, it's just test questions coming from previous tests. So look over all your old tests and make sure that you are studying up on those.
You said that's on Friday?
On Friday.
Okay.
All right. So with that, I have nothing more to say. I'm going to call that good for the day. Stick around if you have any questions. Otherwise, you can have yourself a wonderful day.